So we are going to start part 2 of our review. This is the second page. And we are going to be looking at this rational function. Remember that a rational function is one polynomial divided by another. The first thing that we always do when dealing with rational functions is look at the domain of the rational function. So to find the domain, we take the denominator and we set it not equal to 0. That will, then we factor. So this will factor to x minus 3 times x plus 2 is not equal to 0. And that tells us that x cannot equal 3 and x cannot equal negative 2. So once we know that, we now need to determine there are two different types of discontinuities that can occur in rational functions. You can have a whole, otherwise known as a point discontinuity, or you can have a vertical asymptote. We determine that by now looking at this function and simplifying it down. So we've already got the bottom done. This is x minus 3 and x plus 2. Now we have to factor the top. So I'm going to come down here real quick. 2x squared plus 3x minus 2. I'm going to, my father drinks Red Bull, so that's going to be x squared plus 3x minus 4. Now I'm going to factor that to x plus 4 times x minus 1. X plus 4 over 2 times x plus 1 over 2. X plus 2 times 2x plus 1. I dropped a negative, so that should have been a negative. Pop it up. Bam. Minus 1. All right, so my numerator is 2x minus 1 times x plus 2. And again, I'm trying to determine whether or not these are vertical asymptotes or wholes. So notice that I have an x plus 2 in the numerator and an x plus 2 in the denominator. Those cancel out. Since the factor that is associated with the negative 2 canceled, that means that that negative 2 is a whole. I can now take that negative 2 and plug it into what I have left. 2 times negative 2 minus 1 divided by negative 2 minus 3. That gives me negative 5 over negative 5, which is 1. And so my whole actually occurs at the point negative 2, 1. Since the 3 did not cancel, this is a vertical asymptote. As far as horizontal asymptotes go, we look at the numerator and denominator, and we see that they have the same power in the numerator and denominator. The degrees are the same. So we have a horizontal asymptote at the coefficient, at the ratio of the lead coefficients. So that would be 2 over 1, or just plain 2. X-intercepts, that's the zeros of the remaining numerator. So 2x minus 1 equals 0. X equals 1/2. And then my y-intercept, that's going to be the ratio of the constants. So that's negative 1 over negative 3. So that's going to be 1/3. Now I'm going to take all of this information that I have here. I'm going to come over to this side and I'm going to graph what I've got. So let's just go through this, all of it. We have a vertical asymptote at 3. We've got a whole at negative 2, 1. We have a horizontal asymptote at 2. An x-intercept at 1/2. And a y-intercept at 1/3. Now, if I connect these dots, the only way I can go on this side would be like that. If I did anything else, I would have to cross that x-axis again. Over on this side, I can't be down here because that would require me to cross the x-axis. So over here, I've got to be up in that corner. Next, we are going to find the inverse of this function. F of x equals x minus 1 over 5. Let's say, fix that. There we go. All right, so to find an inverse function, remember that with inverse functions, the domain of the original function is the range of the inverse. The range of the original function is the domain of the inverse. And in order to find an inverse function, what we basically have to do is switch the position of the x and y. So most people find it easier to, instead of working with that f of x, let's just make that y equals x minus 1 over 5. Now to find that's the original function. The inverse is x equals y minus 1 over 5. Notice I took the y and replaced it with an x. I took the x and replaced it with a y. Now I just resolve for y. That gives me 5x equals y minus 1, and y equals 5x plus 1. So what I have there is f inverse of x equals 5x plus 1. So looking at a couple of things about these, let's just graph these two functions on the same set of axes and look at them in a little more detail, even though the worksheet does not necessarily ask you for this. Whenever we look at inverse functions, we are remembering that they undo each other. They are opposite each other. So for every point on this one, the xy point on this one, the opposite yx point is on this one. Here's what I mean by that. So this is a line. If I plug in, let's just look at a couple of points from this real quick. If I plug in 0 for x, then I get out 1/5 for f of x. If I plug in 0 for y, then my x value is 1. So those 2 points are on the graph. Looking at my inverse, if I plug in 1/5 times, plug in 0, negative, my bad, right? If I plug in 0 for x there, I get negative 1/5. If I plug in negative 1/5 for x, that would give me negative 1 plus 1, which is 0. xy, yx. All right? Now, if I plug in 0 here, I get out 1. Because I had 1, 0, I have 0, 1. If we look at the graphs of these two functions, you will see that this graph looks something like that, and this graph would look something like that. The two graphs themselves are symmetric about the line y equals x. That was a bad graph. I'm going to regraph that for you real quick. So I don't have to do any video editing. I'm just going to regraph it. Do this. Let's take this and graph it on here. So like I said, I did not like that graph I was drawing. So I'm going to do a much better graph. Here is x minus 1 over 5. That will be in blue. 5x plus 1 will be in red. And then I'm also going to add the line y equals x in black. And we will zoom 6, just a standard zoom. So there's my one line. There is my inverse line after that. And there's the line y equals x coming in after that. Now the reason I added that line y equals x is because inverse functions are always symmetric about the line y equals x. So there are the three graphs that we have that are interesting in this one. Sorry, the graph at the beginning was not perfect, but that is a much better representation. So there you go. All right, we're going to do a couple of little logarithm expansions. That should be 50 over x, not 50 over 5. So I can take this, and using my rules of logarithms, I can make this into log 50 minus log x, using the fact that that is in the denominator. And that will get you good partial credit. But if you want to get full credit on a problem like this, we must also see that this 50 can be broken down to 5 times 10. Now, the reason I would want to do that is because this logarithm is based 10. So I can actually take more information out of the logarithm. So I could rewrite this as log 10 plus log 5 minus log x. And log 10 is just plain 1. So my final answer should be 1 plus log 5 minus log x. We have the natural log of x plus 3 natural log of 3x. This time we are going to bring these two together. Oops, let me turn my... It doesn't do that stupid focusing thing. So I'm going to first pop that 3 up into the top. That will turn this into logarithm natural log x plus natural log of 3x to the third. Now this is a place where a lot of students make a mistake. This 3 needs to be applied to both the 3 and the x. So this becomes natural log x plus natural log. 3 times 3 is 9 times 3 again is 27x cubed. I can then combine these two and get natural log of 27x to the fourth. Using these rules to solve, I can add 13 to both sides. 4e to the x equals 29. E to the x equals 29 over 4. And then all I have to do is change form. Natural log 29 over 4 equals x.